Grabowska.
Very important.
I was so close. Can you tell us about defining chiral gauge theories beyond perturbation theory?
Wonderful. Well, thank you for having me. I'm very excited to be here. So today I want to talk about defining chiral gauge theories non-perturbatively, or also essentially how to put chiral gauge theories on the lattice. And so this is work that I've done with David Kaplan in 2 papers, initial one in 2015 and a follow-up that just went live a couple of weeks ago. So just for some historical context, parity violation was first seen in the decay of cobalt-60 way back in the 1950s. And so the way that this can be done is, since cobalt-60 decays into nickel, with of course the release of an electron and an antineutrino, that nickel state is excited, and so then very promptly decays into 2 photons. And so what you can do is you can check parity violation with this. Since if your cobalt nuclei is oriented, just with the application of a very strong uniform magnetic field, your electron will decay, and it will decay with some angle. Now, if you look at the parity inverted experiment, you'll still have the cobalt spin is oriented up, but then your electron will decay downwards. So therefore, if in your experiment you see that there is any dependence on the direction that this electron is emitted, any dependence on this angle theta, then you know that parity is violated. And in fact, this experiment was done in 1956, and that's precisely what they saw. Where when they turned on a V field and then let it decay away, they saw an asymmetry that went from non-zero to 0 as you turn the V field off. And they did it for both plus H and minus H. So of course what this tells us, even in the 1950s, that the electroweak interactions have to differentiate between left-handed and right-handed fermions. There has to be some sort of fundamental parity violation in these interactions. And so that's what motivates my work, is this question of, well, we know that parity is violated. We know that electroweak interactions differentiate left from right. But what are actually the necessary ingredients for chiral gauge theories, and the gauge theories that differentiate left from right? And you might say, well, this already should have been a solved problem. After all, we can experimentally test chiral gauge theories. The standard model is a chiral gauge theory. Unfortunately, it's weakly coupled, hence the name. And so experimental probes only really give information about the perturbative sector, the sector where you only care about, let's say, finite momentum gauge field configurations. And you really have no experimental access to the non-perturbative regime. And that is a regime that plays an important role, after all, in QCD at low couplings, that those non-perturbative phenomena are very important for understanding the full structure of your theory. So experimental tests will not give us all of the necessary ingredients for a well-defined chiral gauge theory. So we're only left with theoretical predictions. Unfortunately, the current quantum theoretic description only gives us access to the perturbative sector yet again. Mainly, the only way we know how to regulate chiral gauge theories currently is through Feynman diagrams, dim-reg plus some gamma-5 technology. And there are certain things that you'll never see in perturbation theories, such as instantons. So really, if you want to know the full matter content, let's say, of a chiral gauge theory, you have to find a non-perturbative regulator. There is no other way to get that information. So you can ask, why is this so difficult to do? After all, for a vector theory, like QED or QCD, this has already been done. And so for a vector theory, it comes down to the fact that you have a real fermion representation, which allows you to have a mass. And the minute that you're allowed a mass under gauge symmetries, you can introduce polyvelars, or you can introduce a gauge invariant massive regulator. After all, a regulator needs to have some high mass scale associated with it. And of course, there's a known lattice regulator, lattice QCD, does a beautiful job of completely defining the path integral of quantum chromodynamics. However, things change drastically when you start looking at chiral theories. So, for example, in the electroweak sector, you now have complex fermion representations, and therefore your gauge symmetry forbids a fermion mass term. And now if you wanted to use, for example, polyvelars, you're no longer allowed to, because a polyvelar needs to have some mass scale associated with it, but it also has to have the same gauge symmetries as the fields that it's regulating. So if the fermions aren't allowed a mass scale, neither are polybolars. And so this flows into the fact that there's no known, proven lattice regulator for chiral gauge theories. And now you might think that this is a difficult question, because now we somehow need to balance the fact that we need to control our UV divergences, which require a mass scale, but we also have to do it in a gauge invariant manner, which forbids this mass scale. And so overcoming this is the difficulty in how to regulate chiral gauge theories. There's another aspect to chiral gauge theories that becomes difficult on the lattice, and these are anomalies. So recall that anomalies are quantum violations of chiral symmetries. And so a great way to see this is looking at the 2D QED example, where you simply put massless electrons in a box. So if we take as our initial state that we have a filled Dirac C, where we have some right-moving fermions and some left-moving fermions, and they're in the C itself, so this is our ground state. You can ask what happens if I turn on an electric field and turn it back off. And if I do this adiabatically, one can show that the final ground state, I've popped right-handed moving fermions out of the vacuum, and then popped left-handed moving anti-fermions out of the vacuum. So essentially, I push my left-handed ones into the vacuum, creating holes, and my right-handed ones come out. And you can ask whether this violates any symmetries. Namely, it's interesting whether this violates any left versus right symmetry, since QED couples equally to left and right. So if I look at the total fermion charge, it doesn't change, which is great. U1 vector is preserved, QED makes sense. However, the total chiral charge, so the number of left-handed particles minus the number of right-handed particles, can in fact change. It doesn't have to, but it might. So you could have this U1 axial that's violated, even though your classical symmetry, even though it's a classically protected symmetry. And now the thing that tells us whether U1 axial is violated or not is the depth of the Dirac C. So if you have an infinitely deep Dirac C, such that pulling these right-handed fermions out of the vacuum doesn't deplete the states down here, then you will in fact violate the axial charge. However, if you have a finite number of degrees of freedom in the C, then it is preserved. And so this plays an important role in lattice regulating chiral gauge theories. So you can look at the difference between a perturbative regulator and a non-perturbative regulator. And in our case, the perturbative regulator is just continuum field theory. So in the continuum, we know that there are anomalous chiral symmetries. We know the standard model contains anomalous global symmetries. After all, U1 axial is broken. We see pi 0 to gamma gamma with a specific rate. We see a heavy eta prime, so on and so forth. But it's okay. The standard model itself is consistent if you have global anomalies. However, if you now have gauge anomalies, your field theory no longer makes sense. So there's a self-consistency requirement that requires that all of your gauge anomalies cancel, which makes sense because a gauge symmetry is a redundancy in your theory. So now if you break the redundancy quantum mechanically, the theory doesn't make sense, and this actually shows up as a loss of unitarity. And then lastly, in the continuum you have a chiral symmetry, and this prohibits additive renormalization of your fermion mass. So you can have naturally massless fermions, which are required to have the complex fermion representations. Now things change drastically when you look at the lattice. So the lattice itself has a finite number of degrees of freedom. That's actually sort of why it works as a non-perturbative regulator. However, now that I have a finite number of degrees of freedom, I don't have any anomalies. So what this means is if I have a global symmetry that's anomalously broken in the continuum, I have to explicitly break it on the lattice. There's no other way about it. You have to break it explicitly. However, with gauge symmetries, it becomes more tricky. Because for gauge symmetries, we don't want it to be broken in the continuum, but we have a self-consistency criteria. So therefore, our lattice formulation has to have some sort of road to failure that says if you try and lattice regulate an anomalous fermion representation, or a chiral gauge theory with an anomalous fermion representation, something has to go wrong. And it's only okay if you put down an anomaly-free Fermion representation. And when you make these statements, you can never talk about anomalies. You have to have some other criteria. And this step has proven very difficult to figure out for chiral gauge theories. And then lastly, corresponding to sort of chiral symmetry protection, there's actually a no-go theorem for massless fermions. So if you have a lattice-regulated massless fermion, you can't preserve the full chiral symmetry. So that's in sharp contrast to the continuum. And now, the reason why I think this is an interesting question to ask, or the question of how to put chiral gauge theories on the lattice, is that there seems to be this mismatch between what perturbation theory is telling us and what our non-perturbative regular can seem to do. And so it could be that we're actually missing physics. The fact that the standard model only reveals perturbative chiral gauge theories to us, there might be physics that we are missing and we actually need to find to have a self-consistent self-consistent standard model. And so this mismatch is why I think this question is an interesting one to explore. Okay, so one can ask, when I actually talk about regulating fermions, what do I actually mean? What do I need to find? So the fermion contribution, I can encode it in the path integral in terms of this delta of A, where essentially I've just integrated out the fermions. So for a Dirac fermion, this can be done in a self-consistent, well-defined manner. Namely, the Dirac operator, it maps from the space of left-handed plus right-handed fermions to that same vector space. So now you can write down a well-posed eigenvalue question, find the eigenvalues, integrate out. And for a Dirac operator, you find that your delta V is just given by the determinant of your Dirac operator. This is what is done in lattice QCD simulations. However, chiral gauge theories work differently, as usual. And in this case, your chiral operator, if you had it in this form, which is sort of the naive continuum version of an operator where you only have a left-handed fermion, this operator maps from the vector space of left-handed fermions to the vector space of right-handed fermions. So this no longer has a well-posed eigenvalue equation. And so the best that you can do if you have an operator of this form is to get the modulus of delta. You cannot get its phase. And without additional information, that phase is impossible to unambiguously determine. So the entire name of the game for putting chiral gauge theories on the lattice is you need additional information such that you can determine this delta here in an unambiguous way. Because we know physics and physical results are unambiguous, so we need an unambiguous answer. Okay, so taking a step back, when I was comparing and contrasting continuum physics to lattice physics, I mentioned there was a no-go theorem. And since this plays an important role in how to think about just massless fermions on the lattice, I wanted to briefly touch upon it. So the no-go theorem is as follows. That you will never find a lattice operator that can simultaneously satisfy these four conditions. And the four conditions, and I'll sort of give an intuitive picture of them in a second, the four conditions are that it's periodic and analytic in momentum space, that it reduces to the Dirac operator in the continuum limit, that it's invertible everywhere except at zero momentum, and that it anti-commutes with gamma 5. So the implications of these four criteria is the first, it's simply that you want a local Fourier transform. Sort of makes life easy, and it tends to give well-defined field theories. The next two combine to give a criteria that you find a single massless Dirac fermion in the continuum. After all, if it's invertible everywhere except at zero momentum, that's your masslessness. And then lastly, anti-commutation with gamma 5, it's that your full chiral symmetry is preserved. So if you lattice regulate a massless fermion, you will never be able to satisfy all four of these. And as a quick example, if you just naively discretize your Dirac operator, you would find that the momentum space operator is just this, gamma mu sine of p mu. And now this very clearly violates the third point, as on the lattice, your momentum can only range from 0 to pi. That's actually how it regulates your loop integrals. And now sine of p is 0 at both 0 and pi. So now you violated 3, and this actually gives rise to the famous doubler problem, where if you try and have a single massless Dirac fermion on the lattice, you suddenly generate 16 of them. And so the key point is this: there is no way around this no-go theorem. Any lattice-regulated chiral fermion, any lattice-regulated Dirac fermion, somehow has to violate one condition. And the question is, how do you violate one condition or more conditions and still get a sensible theory? And a solution to this was found right around the same time that the no-go theorem came about, due to Ginsparg and Wilson. And so what they did, this was done in 85, is they said, well, we don't know how to lattice regulate Dirac fermions, but I can construct a lattice theory from the continuum theory by simply doing block spin averaging. So I take a continuum theory, I block spin average, I essentially create blocks, average, and I generate a lattice theory. And then you can say, now that I've block spin averaged this theory, what is the behavior of my operator in this block average theory? And what they find is that their fermion operator actually satisfies this equation. So notice that this violates number 4 in the no-go theorem, in that the fermion operator does not exactly anti-commute with gamma 5. It has this additional term here. And I've explicitly shown the lattice spacing here, because notice that if I take the lattice spacing a to 0, so I go to the continuum limit, I recover anti-commutation. So what this tells me is that it's actually that U1 axial, the symmetry that we want to be spontaneously broken in the continuum, is explicitly violated only at finite lattice spacing. So an operator that satisfies the Ginsparg-Wilson equation will correctly violate U1 axial on the lattice. You can also show that this operator obeys the index theorem correctly, namely the theorem that relates the index of your gauge field to the number of zero modes. And there's also a new symmetry that protects fermion mass from additive renormalization. So finding an operator that satisfies this equation is key for getting massless fermions on the lattice. However, there's one sort of interesting twist on this, is that the solution has the general form as given. And now the thing to notice, and I'm using a chiral form here, that this term that's proportional to A connects left-handed and right-handed fermions. And so what this means is that if you're working with a gauge invariant operator, if you want a gauge invariant lattice theory, you have to have the left-handed and right-handed fermions have the same gauge transformation, which seems really, really bad. Because the entire point of chiral gauge theories is that your left-handed and right-handed fermions have different gauge transformations. So these things seem very much at odds. And I'm going to come back to this point later on to show that it's actually okay. We can get around it. But first, I want to tell you how we get massless Dirac fermions on the lattice. Because even though the no-go theorem was written down in 81, Ginsparg-Wilson was written down in 85, an explicit solution in the Ginsparg-Wilson was not written down until the mid-90s. And that was done via domain wall fermions. So the way that domain wall fermions work is you need some sort of new mechanism that'll give rise to naturally light fermions in your lattice theory. So what you can do is you can introduce an extra dimension defined by S here. And it's going to be a compact extra dimension going from minus L to L. And then introduce 5D fermions such that their mass has this domain wall shape. That I go from negative M to positive M halfway through the bulk.
Sorry, can I just ask,
Yeah.
looking up, so this, when you wrote that equation before, I'm not familiar with this Ginsparg-Wilson kind of
Yeah.
much, so there are no higher order A corrections, that's really an exact relation,
Mm-hmm.
and so that exact relation has some of the properties of a symmetry relation. And it's important that there not be any higher order
Yeah.
A corrections, okay.
Yeah, so this is exact, and it's important that the chiral violation is only in the U1. You don't break any other chiral symmetries.
So is this really associated with some exact symmetry on the lattice?
Yeah, so I don't know if I can see over here. So the symmetry, I believe, goes like, there might be a minus sign. I can remember it. So I think that the rotation sort of looks like that. Oops, sorry. Something like that, where psi and psi bar transform slightly differently.
So it's a discrete symmetry, is that right?
No, I would still say it's a continuous symmetry. It's just the fact that on the lattice you can treat psi and psi bar differently. And so you can show that when A goes to 0, this is, you recover the U1 transformation on it.
But that doesn't depend on the parameter, that's what I meant by.
It doesn't here. Sorry, I mean, so sure, I mean, you can have some alpha.
Okay.
Okay.
Something like that. Okay.
Yeah.
Okay.
Yeah, so the important thing is that it's psi and psi bar have different transformation properties.
Okay. Thanks.
Yeah. Okay. So with the addition of this 5D fermion master, now that you have this domain wall set up, where your mass jumps from negative to positive, you'll find that your spectrum actually contains light degrees of freedom that are localized on these boundaries. Mainly because you have this discontinuous jump, and so therefore you can get localization at that jump. And the important thing is that the light modes, the right and left-handed fermions, are exponentially localized on those boundaries, which is why they're light, because essentially the overlap, which is proportional to the mass, is exponentially suppressed. You will also have heavy fermion modes, bulk modes, that are delocalized into the bulk itself. And those will play an important role for the U1 axial. So essentially domain wall fermions, even without a gauge field, give you a way to get light degrees of freedom. However, we do want to replicate the U1 axial anomaly on the lattice. And so we somehow have to introduce gauge fields such that that is done correctly. So to introduce gauge fields, while we had 5D fermions, you're going to couple them to a 4D gauge field that's independent of S. So essentially my gauge field is the same on each S slice. And that way you see clearly that both the right-handed and the left-handed fermions see the same gauge field. So this is a vector-like theory. And you can show that if you integrate out the heavy bulk fermions, as you're always allowed to do with heavy modes, they completely decouple apart from a Chern-Simons operator. And this is the Callan-Harvey mechanism. And the important thing about this Chern-Simons operator is it sources a current that essentially carries charge from the left-handed wall to the right-handed wall, or vice versa. And if you think about what the light fermions see when they see this charge coming towards them, it actually looks like a U1 axial symmetry breaking. So from the perspective of the light degrees of freedom, you have U1 axial, explicit U1 axial breaking. This is also known as anomaly inflow in certain spheres. Good. Okay, so now that we seem to have a construction that gives us a vector-like theory of light fermions with the correctly reproduced U1 axial, you can ask whether you can actually derive the effective fermion operator such that you can then check whether the Ginsparg-Wilson equation is solved or satisfied.
Sorry.
Yeah, no worries.
In the other setup, the usual domain wall fermions, this gauge field is a dynamical gauge field that you're introducing in addition to the usual?
No, this is the usual one.
Okay.
So
this is the domain wall fermion.
Yeah, this is still the domain wall fermion. Okay. We'll modify it later for chiral gauge theories. Yeah. So the important thing to note is that this is actually the way that you get lattice QCD simulations. It's using exactly this construction. Okay, so if you want to find the effective fermion operator for this construction, so you can see whether the Ginsparg-Wilson equation is actually satisfied, you first have to take the limit of an infinite extra dimension. And the reason why is, remember, I had pointed out that the left-handed and right-handed modes are exponentially localized, so their mass is exponentially small. And it only goes to zero if I actually push the two walls off to infinity. So to construct this effective fermion operator, I somehow have to work in a construction where I have an infinitely large extra dimension. And it's highly non-trivial. It's actually beautiful when this was first derived, is that you can actually integrate out the heavy modes, all of the modes that are here in the bulk. You can integrate them out even though there's an infinite number of them. And if you do that, you'll find the effective fermion operator for the modes that are localized on the boundary. And this is just it. This is the overlap operator. So it's just 1 plus gamma 5 epsilon, where epsilon is just the sign of the Hermitian matrix that's given here. And so to derive this, I've done a couple things. I first set the positive mass equal to 1, so this mass is positive 1, and I've taken this negative mass to be infinite. And that's totally okay to do. You can actually show that you still reproduce all of the same behaviors between finite and infinite. And then this dw is just the Wilson operator. It's the naively discretized fermion propagator plus an additional term to get rid of some of the doublers. But the important thing that I really want to get at is that this operator obeys the Ginsparg-Wilson equation simply because this epsilon is a sine function, and so it squares to 1. And that's really all you need to satisfy the Ginsparg-Wilson equation. If you can show that your operator can be written in a form of 1 plus gamma 5 times something, as long as that something squares to 1, you satisfy Ginsparg-Wilson. Good. And now the question is, we know how to do this for vector theories. This was done in 95 and 98. But can we reproduce this for chiral gauge theories? Can we derive an operator of a similar form such that we still satisfy the Ginsparg-Wilson equation, but we now also have that our left-handed fermions only couple to the gauge field and the right-handed ones do not? And so the first attempt to do this was done pretty much right after domain wall fermions were constructed. And so what you want to do is, well, if I only want left-handed fermions to couple to the gauge field and not have right-handed fermions coupled, why don't I just localize the gauge field around the left-handed brain? Right, so essentially the left-handed fermions are the only fermions that see A, and then outside here, I'm just going to turn off the gauge field. And the right-handed fermions will never see the gauge field. And the problem with this is that the theory is not gauge invariant. Because essentially, as you're stepping into the extra dimension, right, that 5D fermion has a derivative coupling in X of the form like this. This is just the standard fermion kinetic term. And now, if you break this apart into discretized extra dimension, you'll see that you'll have coupling from a fermion sitting at S is equal to n plus 1, and S is equal to n. So essentially, I have a coupling between a fermion that's sitting here and a fermion that's sitting here. So that's very clearly not gauge invariant, because this fermion transforms under A, this one does not. So what you need to do to have a gauge invariant theory is you have to add a Yukawa-like coupling at this discontinuity, so some sort of Higgs mechanism. And now you can simulate this, you can put this on a computer and see what happens. And it turns out the spectrum is vector-like. And the reason why is that introducing this Yukawa-like coupling at these boundaries actually generated new domain walls. And so you'll find, again, that you'll have a right-handed fermion sitting here and sitting here. And so then your theory, your gauge field, again, will see a left-handed and a right-handed fermion. So this is a vector-like theory, and this construction does not work. However, you can think about maybe doing this sort of localization of the gauge field in a gauge invariant way. And so this is work that I did with Kaplan last year. And so the idea is, again, take this domain wall fermion construct But instead of very sharply localizing the gauge field around the left-handed brain, have the gauge field flow into the extra dimension in a gauge invariant way. So that my gauge field at here, A, will somehow change into A star in a smooth manner. And you might ask whether it's possible to do that flow in a gauge invariant way, and in fact it is. And it's called, the equation you use is called gradient flow, which is given here. So essentially you flow the gauge field using its own equations of motion. And since this is a gauge covariant flow equation, A and A star transform identically under gauge transformations. So you can maintain gauge invariance. However, gradient flow will damp out the high momentum modes of the gauge field, but only the physical degrees of freedom, not the gauge degrees of freedom. And I'll show what I mean by this in 1 second. So the important thing about this construction is since you're flowing with this deterministic flow equation, the gauge field in the bulk, and particularly A star, which is what your right-handed fermion sees, is completely dictated by the gauge field that you place here at the left-hand fermion. And so this A is actually the integration variable in your path integral. So everything is determined in terms of that, as would be expected.
So you're going to talk more about this? I mean, it's, I see. DS, it's gauge invariant because you're only allowing S-independent gauge transformation.
Mm-hmm.
Right?
Yeah, so since it's still a 4D gauge field, and since it's as you say, my gauge transformations are only S-independent. Yeah. Which is fine, because if I want to reduce down to a 4D theory, I don't want any S-dependent gauge transformations. I don't want to know anything about S. And these sort of gauge transformations are the exact same way that you do in the vector case. Okay. So as a quick example about how gradient flow works and how we can think about it in terms of a heat equation, I can again look at two-dimensional QED. It's just a very useful theory to look at. So in two-dimensional QED, my gauge field can decompose explicitly into a gauge degree of freedom and a physical degree of freedom. And what I mean by gauge and physical degree of freedom is that if I do a gauge transform on A mu, omega will shift, but lambda is fixed. It doesn't change. So therefore, if I actually think about the physical field that I would see in experiment, it's this lambda, not omega. And now both of these degrees of freedom have their own flow equations to satisfy. And so lambda, my physical degree of freedom, satisfies this flow equation, which is just the heat flow equation, where lambda is just some mass scale needed to make everything have the correct dimensions. But notice that my gauge degree of freedom doesn't flow. It automatically satisfies the gauge covariant flow equation as one would expect. So if I look at the profile of both omega and lambda in the extra dimension, as I go from 0 to L, so from left-handed fermion to right-handed fermion, my gauge degree of freedom is completely unaffected, but my physical one is damped out. And so essentially what this means is that my right-handed fermions see the gauge field, but it's with exponentially soft form factors. So it is only for exponentially low momentum gauge fields that the right-handed fermions can interact at all. And so one could hope that maybe they would then decouple if I take the extra dimension to be infinite. Okay, so now that we have this construction, recall that the important thing for getting chiral gauge theories, one of the important things for getting chiral gauge theories on the lattice, is you have to have some sort of road to failure for anomalous fermion representations. And this construction has that, and I will go through exactly how it does it now. So, similar to the vector case, I again have heavy bulk fermions, and I can integrate them out. And they'll once again generate a Chern-Simons term. So if I have my theory here, where I have my light mode that's localized, my heavy fermion that's delocalized, and then my gauge field, my bulk gauge field, if you're living in the bulk, If I integrate out the bulk fermions, everything stays the same. I just generate this Chern-Simons term. And that's the only effect of these heavy bulk fermions, is that they don't completely decouple. They leave over some residual interactions. Yes?
Sorry, so can you go back just for a second?
Mhm.
So is the claim that, I mean, it's not obvious to me why this gauge degree of freedom being unaffected is important for the fermion spectrum.
Uh-huh.
I mean, I would have expected something like you would want to do a calculation now in this thing and find out whether there was, the suspicion, at least I would have, is that even if you turn this thing off softly, you would still have some fermion zero mode that might be bound now to this left-handed brain, you know what I mean, and restore a non-chiral spectrum, you know what I mean? Since that's what happened when you had the sharp wall,
Right.
there that was sharply localized to your sharp boundary.
Mhm.
Here you have some soft wall.
Yeah.
What you want to show or argue is that you do not have a similarly, some zero modes that are somehow bound to that.
Right. So that is something to eventually get. I'll sort of argue why we're not too concerned about it. Actually, I'm going to do it now. But the big thing is, so with the sort of waveguide model, we just have A and 0. That has to be checked numerically. There really is no way to get at that spectrum otherwise. And so that is something to be done, and hopefully it is something that is being done right now. But there is a difference in our construction versus that construction, and the major difference is, let's see. So these Yukawa couplings, right? They since you put them in to maintain gauge invariance, but they couple left to right. And sort of in a sharp way, where it's sort of natural to think about this as some new domain wall.
What is that's fine, but then what is, I guess I didn't understand what is even the intuition, or why should I even think that having this, I guess, why is this having this gauge invariant turn off a good thing? I guess you're just saying that it's a way of turning it off without putting in explicit left-right coupling.
Yeah, I mean, so it's a way of turning off the dynamical degrees of freedom and maintain gauge invariance, which is
right. So you're going to say more about why it has a chiral fermion spectrum?
Yeah. So and sort of the way that I want to get at it is via anomalies, actually.
Okay.
It doesn't. I mean, so this will not be fully resolved until someone actually numerically simulates it, which is a whole other question. But the fact that there is a road to failure is very good, and so I'll explain that.
Okay.
Yeah.
Going back
How far back?
let me go back. So the gauge invariant part
Yeah.
of A is going to 0. So how can you generate a Chern-Simons term?
Sorry. So the gauge, right? So the gauge invariant part is going to 0, and the Chern-Simons. Can I pause that question for 1 second, show you how it actually does it, and then we can come back to it?
Sure.
Okay. So, generically, how I think about these Chern-Simons action is in the 5D theory, it's allowable to write it down just based on power counting. And so if I work in 2 dimensions plus an extra dimension, the Chern-Simons action that I would write down is this. And a couple important things to note about it is the Chern-Simons only depends on the sign of the domain wall maps. It can depend on the magnitude just by dimension counting. There's the fermion contribution, which changes sign, essentially because lambda changes sign, which I now use lambda to also mean the domain wall height. And I also introduced polyvalars to control some other divergences. So this is just a Chern-Simons action that I can always write down for a theory that is in 5 dimensions. And you can ask whether this has any, if it's non-zero or zero, whether it plays any important role. But the important thing is that this approximation only is valid far away from the wall.
Sorry,
Yeah.
What 3 dimensions are these? Sorry.
No, it's okay.
I'm
So
not understanding at all what you're doing.
I again want to reduce down to 2-dimensional QED. So
Okay, we're doing 2 dimensions.
yeah, so it's
Sorry, so this is the X dimension.
yeah. So I have 2 dimensions plus this extra dimension.
Okay.
Yeah, I apologize for not making that clear.
Sorry, maybe you might have said it.
Okay. So now, if I look at this Chern-Simons term for 3-dimensional QED, it's of this form. And so the reason why I want to come back to this question of if I'm decaying away the gauge invariant term is that this is my gauge invariant term right here. So it still couples, and this is my this is my gauge. This is my gauge degree of freedom. This is my physical degree of freedom. So nothing prohibits me from writing down a Chern-Simons term. It just depends on whether it's 0 or not. And so normally the Chern-Simons term couples. It's normally 0 if you have a gauge invariant theory. But the reason why ours is not 0 is that flow, essentially, one of the derivatives acting in here can be a derivative in S, which then picks out the fact that lambda has this exponentially decaying form. So if you write down this Chern-Simons action, there's no gauge field in the 3rd dimension, but you do have this exponential decay. So this is actually non-zero, and even more so is that it looks non-local. So if you look at this 2-point function here, gamma, it has this form, or it has a delta function, and then an exponentially decaying term, which is actually what happens when you have the flow. And I've defined mu in terms of the domain wall height, and L, which is the length of the extra dimension, and then I've introduced this C, which just tells you how quickly you flow. And now, notice that when I turn off the flow, so when I take C equal to 0, mu goes to infinity, gamma vanishes, and your Chern-Simons term completely disappears. And so this is what I would expect for a vector theory, that I shouldn't have explicitly this sort of Chern-Simons term that would seem to couple my gauge degree of freedom to my physical degree of freedom. So I'd argue the fact that our construction has this means that we're not really getting a vector-like theory. And now this Chern-Simons plays an important role for gauge anomalies, since our 2D theory is non-local with this Chern-Simons operator. Essentially, if this Chern-Simons operator is non-zero, your 2D theory that you're wanting to find is non-local, which is bad. We want to write down the effective action for a local theory. We know that chiral gauge theories in the continuum can be local. So the question is whether we can ever make this Chern-Simons term be 0. And the important thing is that if I introduce multiple fermion fields, this Chern-Simons prefactor takes on this form, where E squared is just the fermion charge, and then lambda is just the domain wall height for that fermion. And now, the sign of lambda actually determines the fermion chirality. So I've always been drawing my domain wall going from negative to positive, and I had a left-handed fermion here and a right-handed fermion. I can actually show it. From negative to positive, and I'd have left-handed and right-handed. Now if I switch my domain wall, so this becomes positive, this becomes negative, I localize a right-handed fermion here and a left-handed fermion here. So this is actually just the fermion chirality. So now if this prefactor is equal to 0, this non-local Chern-Simons is also 0.
So maybe I didn't understand something, but somehow, so what is it that distinguishes, so if you integrate out these fermions, you're going to generate a lot more than just this. You're going to generate a huge non-local mess, right?
So...
My question is, or maybe I'm misunderstanding, but my question is, if that's right, what is it that singles out this term?
So there's sort of two questions. The question is whether any of the mess that you generate is a relevant operator or not. So if I don't have the flow at all, if I completely turn off the flow and I go back to the vector case, the only relevant operator that I find when I integrate out the heavy modes is the U1 axial violation.
By relevant, what do you mean by relevant?
Dimension 4. I mean, it has the correct dimensions for your theory. So essentially, I can always write down, these operators, that'll contain more gauge fields, so on and so forth, but none of them are going to have, they're all going to be higher order operators. And so
You're
therefore,
doing some derivative expansion.
yeah. And so then if I can flow slowly enough, then all of those are going to be irrelevant. So the argument is that really this is the only operator that will get generated by the heavy modes. And with no flow in the gauge field, that was shown conclusively by Callan and Harvey.
So this one is not really non-local. There's those 1 over boxes. Is that somehow, that's a projector or something, so that it's not really non-local? This is secretly local.
So I would say the 1 over boxes mean that it is non-local.
Okay, then I guess I don't understand. But you're still saying in some derivative expansion this is the leading thing. That's
So I would say that when I write down, okay, so sorry, maybe derivative expansion is not quite what I was going for. Now, when I was writing down, so for example, I could write down terms that include multiple gauge fields, right? But those, since the gauge field always comes in with powers of 1, that's always going to be a higher order operator. And so therefore those will all be irrelevant operators. So I'm not necessarily doing an expansion in sort of the smoothness of the gauge field, it's just in terms of the gauge field itself. Right, so if I think about, and it's the exact same way that in 4 dimensions I can't write down a sidebar size square term, that's a higher order operator.
So you're expanding in small gauge fields?
No, I'm doing normal
I guess
power.
I'm just trying to understand what distinguishes this term. You will generate eventually an infinite number of things.
Right, but they will all come suppressed by a power of lambda. Right, because lambda is my mass scale.
So you're doing an expansion inverse powers of lambda.
Yeah, and so it's sort of it's sort of the normal power counting that I would think about when yeah.
Okay.
Yeah. Okay. So the important thing is that the theory is local if this prefactor vanishes. And since this is the fermion chirality, and this is the gauge charge squared, the criteria that the Chern-Simons operator vanishes is actually exactly the same as the criteria for gauge anomaly cancellation in the continuum. So this now gives us a road to failure for this construction, where if you want a local theory, a local 2D theory, you have to put down fermions in an anomaly-free representation. If you use an anomalous representation, you're going to get non-locality. And this actually persists in higher dimensions. So the summary so far is that if we couple domain wall fermions plus a gradient flow gauge field, a gradient flowed gauge field, we claim this gives you a lattice-regulated chiral gauge series. Mainly because you get massless fermions that are localized on the boundary here, here, and here, and the limit of extra dimensions. The fermions on the far boundary couple with these exponentially soft form factors, so that when I take L to infinity, they go completely to 0. And then lastly, our road to failure is that if you want locality on the lattice, your charges have to satisfy the same criteria as your gauge anomaly cancellation in the continuum. And there's a couple of open questions that I want to touch upon briefly. The first one is whether the mirror partners actually completely decouple, and if they don't, what are the physical implications? And then also whether we can derive an effective fermion operator analogous to the vector case, but for this chiral construction.
Question?
Yes. Yeah.
So you can do this construction for if the gauge coupling is 0, I think, no?
No, I don't think so, because if your gauge coupling is 0, then your gauge field is completely decoupled.
Yeah, but I mean,
And so, I mean, so then you would
I just
just...
want to understand if there's any perturbative test of this, like the spectrum, I guess I'm asking spectrum of weak coupling then, right? The leading order in the gauge coupling. Is there a test of this that you could do perturbatively? By doing some KK reduction?
Yeah, so the KK reduction without the gauge field is completely done. And you can show that it's rigorous, and the left-handed and right-handed modes are protected topologically. So, yeah, which doesn't really make sense with gauge field. But generally, if you turn off the gauge field, you can show that the left-hand and right-handed modes are you can never generate a mask for them, mainly because you have this symmetry that protects them. There is something that you can do perturbatively for this construction, which I will get to at the very end. And so maybe that will address some of your concerns.
Could you say
Yeah.
a little bit more about what you mean by local? I mean, overlap fermions are not local at non-zero lattice.
So they're...
So,
I'm not sure I agree. I mean, so they're as local as you can...
they become local in the continuum length.
Mm,
The
I mean, so,
interactions
but
are
the-
not localized on one length.
So
finite lattice spaces.
I think... So if you take m to 1, I thought you could localize them fairly well. And it's...
Well, fairly well, a finite number of lattice spaces, if they're 0 and continuum.
Right.
So they're not strictly local at finite lattice spaces.
Right, they're, I guess...
So I'm wondering what you mean by local when you say this.
So what I...
You mean local in the continuum on it, or you mean local at finite lattice spaces?
So I would mean in the same sense that overlap operator is local in the in the same sense that the overlap operator is local.
Okay, so that's in the continuum.
Mhm.
Okay.
Yeah, though I will say that those are two different things, right? I mean, because if with the overlap operator, right, it's sufficiently local at finite lattice spacing. If you had this turn Simons, it would not be sufficiently local in any sense of the word. So that's really what I mean. Okay. So with gradient flow, if I this question of whether the right-handed fermions completely decouple, one can notice that the gradient flow equation, since you're flowing with the equations of motion for the gauge field, actually has multiple attractive fixed points. So case in point, the instantons. And so the flow will not affect these instantons or these topological gauge configurations. So therefore, A and A star will both see them, or will both have these sort of topological configurations, and therefore the right-handed fermions will couple to these configurations. And one has to ask whether this is actually a problem in the theory if your right-handed fermions don't decouple from them. So we can look at what happens at both weak coupling and at strong coupling. So at weak coupling, the only important topological configurations are single instantons, denoted here by green dots. And so since these are exact solutions to the flow equation, they are unaffected by the flow. And both left-handed and right-handed fermions see them. And since there's a correlation between the zero modes here and the zero modes on the left-handed brane versus the right-handed brane, you can exchange energy and momentum between the two branes. And you might ask if this construction is taken to be physical, if these right-handed fermions were actually required to be a part of your chiral gauge theory, is this a problematic coupling? And normally we would say, well, energy disappearing, into the other brane is very bad. But these are highly suppressed processes, right? Because they're done via instantons, and so they're exponentially suppressed, and so it'd be difficult to observe this phenomena. So maybe at weak coupling you're okay. Now if you go to strong coupling, you now have to not only care about instantons, but also anti-instantons, so these pairs. And now there what happens is instanton anti-instanton pairs do not satisfy the equations of motion. And so actually as you flow, these pairs will all annihilate away until you're left with just 3 instantons again. And so the question here, there's sort of 2 questions you could ask. Whether the 0 modes that are on this wall are still somehow correlated with the 0 modes on the right-handed wall. And if there is no correlation, then there is no exchange of energy and momentum. So this will essentially not be really detectable in an experiment because you won't have disappearing energy. There's also the question of whether this is actually an extensive process and whether you could write down contributions to the action such that these 2 coupled. But that is an open question. Yeah.
So I mean, conceptually, I think historically people thought that the demonstration in in QCD that instantons violate U1, that convinced people, even though in the this is really dominated by the infrared and you don't really know what's going on.
Yeah.
I think the philosophy was that if you find any effect that violates a symmetry or some principle that's really sacred, then it's violated, even if it's not under full control, right? So I'm just wondering here, it seems like in the semi-classical approximation, which absolutely is not good, but you do see, this, as you said, this transfer of energy between the sectors. So doesn't that doesn't worry you? That you don't think
it does and it doesn't. I mean, there's sort of other reasons why it doesn't worry as much. So the thing with QC and the U1 axial anomaly is that, I mean, it has large-scale effects. I mean, the eta prime being heavy it's a big effect, right? It's not slightly heavier, it's as heavy as the baryons. So the thing that I don't know is whether there'd be some sort of corresponding thing, where if the process for having energy sort of disappear is exponentially small, then I don't think that's quite analogous to the QCD case with the eta prime being heavy.
I thought in both cases you're just doing a weak coupling expansion, and in both cases it's just that the weak coupling expansion breaks down because the coupling is not weak.
No, so I don't think that you can get at the eta prime doing the weak coupling. You have to do a semi-classical, which are for me 2 different things. So I mean, because you're not going to see instanton effects if it's weakly coupled. So yeah, I don't think so. We can definitely talk about this more because I'm not quite sure how to address it fully yet. Okay, so just to finish up, what I do want to talk about lastly is, these topological effects are curious and interesting, and we really don't know how to deal with them because, as Marcus points out, there are a lot of unanswered questions about them, and I don't know how to address them yet. So that is a big question mark about this construction. But putting that aside for a moment, I do want to show that you can derive an effective fermion operator and show that it satisfies the Ginsparg-Wilson. So replicating what was done in the vector case, we can derive a d-chi that's the effective fermion operator for the massless degrees of freedom in the limit of an infinite extra dimension. And essentially, you just have to take the large L limit of this formula, where this h of s is the Hamiltonian that translates you in the extra dimension. So essentially the Hamiltonian that steps you from the left-handed brain into the right-handed brain. And this depends on A. And the interesting thing about this operator is you know that it satisfies the Ginsparg-Wilson, namely because the eigenvalues of H are real. So this will either be go this entire object will either go to +1 or -1 in the limit of infinite L. And so it actually squares to 1. So this operator, even in this sort of not fully analytic form, actually satisfies the Ginsparg equation. And furthermore, you can derive the analytic form for a very special case. This special case has its own problems, but it's just nice to have a physical operator to look at. So the issue is that it's really hard to take that large L limit analytically because of the form of the transfer matrices. So what you can do is you can use the abrupt flow approximation, where you just assume that the gauge field is essentially constant for half of your space, and then abruptly changes to A star. And there are problems, particularly problems that you were worried about before with generating higher order operators that I'm not going to touch on here, but this actually, it does come to play here. But even though this is perhaps not the best approximation, it does get us an operator that we can look at. So if I assume that A and A star have the same topology, which is a fairly good assumption for continuum gradient flow, not so much for discrete gradient flow, I find that I find a d-chi of this form, where now epsilon is the sign function of the Hamiltonian for a gauge field A, so essentially the Hamiltonian that this left-handed fermion sees. And then epsilon star is the Hamiltonian that the right-handed fermion sees, so the Hamiltonian with the gauge field A star. And so this looks like a very weird operator, so I want to show two key properties of it. So the first is the continuum limit. So you can ask, how can we be sure that we have actually successfully coupled left-handed fermions to one gauge field, right-handed fermions to another gauge field, and not introduced any additional couplings? So if I take the continuum limit of that operator, which can be done, I find that my left-handed fermion only couples to A, my right-handed fermion only couples to A star, and there's no terms that couple left-handed to right-handed. So essentially, I have not set up a new domain wall at these boundaries. This operator preserves gauge invariance because A and A star transform identically. And if A star is pure gauge, then my mirror partners decouple completely. And there's sort of two caveats there. This abrupt flow might actually change some of the power counting in here. But I can maybe make A star pure gauge if I use a discretized flow equation, as topology on the lattice is poorly defined. And that's actually an open question, is if I use a discretized gradient flow or a Wilson flow instead of this continuous flow, what is the form of A star? Does it actually have to have the same topology as A? And then lastly, the question of the phase ambiguity. Remember that earlier, the very beginning, I had mentioned that one of the key things about getting chiral gauge theories on the lattice is how to define that phase unambiguously. And so in this construction, that's done precisely. So if I treat this extra dimension as an my imaginary time, which I can do as my Lagrangian is only linear in S, it only has a single derivative in S in it. What happens is that if I treat this extra dimension as my time direction, taking the infinite L limit, I essentially project onto the ground space of the Hamiltonians defined here, 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 and here. And so essentially, delta A can be written in the following. And I know that this is sort of going quickly because I just want to get at the fact that there's no phase ambiguity. So essentially, I can write this delta, which tells me everything about my fermion contribution, as the overlap of the multi-particle ground states of these Hamiltonians here. So it's essentially in this form. And I won't have more time to prove it other than saying that, but this can be shown rigorously. And now if I think about where a phase ambiguity would come from, it would be by rotating the eigenbases of these different Hamiltonians. However, since I have a compact space, and essentially I can go all the way around, notice that a rotation on the basis, let's say, of HI, is completely canceled out by a rotation here. So essentially, because I can sort of write this in this Hamiltonian approach, there is no phase ambiguity. My phase is completely determined by physics, not by choice of basis. Okay. And so with that, I just want to summarize that finding a way to control these UV divergences of chiral gauge theories is actually key for understanding the standard model. Namely, that we really want to find a self-consistent standard model. So our proposal combines domain wall fermions and gradient flow to give you a lattice-regulated chiral gauge theory. The mirror partners, so those right-handed partners, decouple because they get exponentially soft form factors. We have a road to failure for anomalous fermion representations, namely locality. The effective operator that we derive in this infinite L limit obeys the Ginsparg-Wilson equation, so it'll have massless fermions, it'll reproduce the U1 axial correctly, so on and so forth. And it also has an unambiguously defined phase, and they're at correct continuum limit. However, there are many unanswered questions, some of which were actually raised here. But the real question that I want to get at is that we might be missing physics in the standard model because of non-perturbative chiral dynamics that we can't access experimentally. Thank you.
To localize gauge field, could you use dilaton?
Use a dilaton. In what sense?
Well, some profile to change the gauge calculator.
So you're thinking if I would just have my gauge field in an S-dependent gauge coupling. So I believe that has been looked at. And I don't believe it has been successful. Namely, I think that they didn't really find sort of a road to failure for doing it that way. But that's just a sense of mine. Yeah, that's pretty much all I would have to say on it. Yeah.
I'm a little bit worried about the dependence of this on A and A star having the same topology. Because if they're essentially lattice spacing scale instant times for A,
Yeah.
I think they could be
DKO.
pushed to basically collapse down rather than up and getting to A star.
So the thing
Basically lattice artifact.
Right, so this is sort of something that David and I are still thinking about. Normally I thought that any time you cool, you will always lose topological charge. That you can't sort of generate new ones. And furthermore, since topology is not well defined on the lattice, I would imagine that if you cool sufficiently, you're always going to lose topological charge. So so here's the thing, but I know that some people do add this additional term in their action that sort of keeps instantons from dropping out of the lattice. And the thing that I don't know is whether that does it if you would flow sufficiently far. So I agree that the question of lattice artifacts for topology is something to be concerned about, because we could actually write down so, what am I trying to get at? I guess I agree that your choice of discretization and your order A effects can change how your instantons grow or shrink or so on and so forth. What I don't know is whether you can find an action such that if you flow for infinity, for an infinite amount of time, whether you can preserve topology on the lattice. Mainly because topology is ill-defined. So the question is whether your Wilson flow has any other fixed points at finite lattice spacing. And the important thing is we take the continuum limit after we flow for an infinite amount of time. So, but I agree, this is something to be concerned about, especially if you take two different discretizations and they give you different topology for A star, you have non-universal behavior, and that's bad. Yeah. Other questions?
Let's think about it again.
Yeah. Sorry for going over.